Okay, first question says a small stone is dropped from a height of 25 metres above the ground. You want to start with a diagram with these questions. Well, pretty much every question in mechanics. So this stone is dropped from a height of 25 metres. Also set out SUVAT and think about like what we know. You're going to have to choose a direction to be positive as well. And I actually think for this question it makes sense if, because the stone, after it's dropped, because the stone would be falling down, it would be accelerating this way. I'm going to choose that way to be positive. So just so I can not lose track of the values, I think it's nice if you just, next to your SUVAT, also denote which direction you choose to be positive. So if it starts here and it travels 25 metres, in that direction, the displacement is going to be 25, because it moves 25 metres that way, and that's the way I'm choosing to be positive. It starts from rest, it's dropped, isn't it? So the initial velocity, we know to be 0. And it says find the time taken for the stone to reach the ground. So it doesn't seem like we're actually given that much information. We know it travels 25 metres, it starts at rest. We want to figure out what the time is. But obviously as well in this question we've got to remember that because it's moving due to gravity, acceleration due to gravity is 9.8 metres per second squared. So we can say A is equal to this. And we want to find the time taken. So we actually don't care about the velocity for this question. So we can look in our formula booklet and look at the SUVAT equations. We're looking for the one without V in. And we can say, well, S equals UT. Plus a half AT squared. And then we can substitute in the values and solve to find out what we need. Okay, so S, the displacement will be 25. The initial velocity was 0, so that first term becomes 0. Plus a half, acceleration is 9.8. T squared. Solving the equation to figure out time, because you want to find the time for the first part. And we get 25 equals 4.9 t squared, so divide by 4.9. And then take the square root. We don't need plus or minus, because obviously with this being time in the question, negative time doesn't make any sense, does it? So let's take the positive square root. Okay, square root is 25 divided by 4.9. I'm getting root, 5 root 10 over 7. If you look at the mark scheme in mechanics, obviously if it doesn't say the exact answer, we quite often work with decimals. General rule of thumb, I would use 4 significant figures, unless told otherwise. So 2.2587, so 2.259 seconds to reach the ground. Okay, the next part of the question says find the speed as it reaches the ground. So clearly we're still sort of working in the same model. Sometimes on the SUVAT questions it'll be one stage of motion and another stage of motion, so we need a new diagram. But we're started here, we've travelled 25 metres, we want to figure out what the velocity is now. We can use any equation actually, because we know all of the values, like 2.259. The only one we don't know is V, so we could use V equals U plus AT. As long as we trust that this time value is accurate, the time it takes to get here is 2.259. If you didn't want to use that one, you could use other equations to avoid that time value, but I'm confident in my calculation. So I would say therefore V would equal U, which would be 0. The acceleration is 9.8, and the time that it was accelerating for is 2.259. So if we multiply our answer by 9.8, that gives us 22.13514 units for velocity as meters per second. The last part of the question is more of a comment, it's worth 2 marks. It says, a large package is dropped from the same height as the stone. Explain briefly why the time taken for the package to reach the ground is likely to be different than that from the stone. So in this question, you maybe want to draw a diagram, but you definitely need to write some words and think about like what's going on within, what's changed with the question. And the fact that it's saying it's a large package is a bit of a clue on this question. Like, now this is something that we'll see in another part of the mechanics course. We haven't done that much of yet. You'll have done some of it last year. Like, we noticed in this question, because we modelled it as a particle and we've ignored air resistance, we didn't think at all about any of the forces that were acting. Like, in reality, when something falls, the reason that it falls is the weight pulls it down. But obviously, there's another force that we've completely forgotten. And like, if something falls with this acceleration of 9.8, we're ignoring air resistance there, aren't we? And like, in reality, there'll be a resistance force, air resistance. And what the effect that the air resistance will have is that this acceleration will not be as large. And another way, an even better way of describing it, is you could think about the resultant force. Like, if I say downwards, the resultant force would equal the mass times acceleration. But now the resultant force would be mg minus the air resistance. So because the resultant force would be lower, in other words, the air resistance would be included, the acceleration would also be lower. Okay, let's think about the way that we can write that, sort of what we've discussed, to give us those 2 marks. So we can say air resistance would reduce the acceleration okay, and then we could say time taken would be longer. You could also mention the fact that if you drew this force diagram out, the resultant force looking at the mark scheme, it doesn't mention forces, apart from like the air resistance specifically, but it doesn't. You could say also the resultant force would be lowest, the acceleration would be less. Okay. Next question, we're thinking about the lift, which is travelling upwards. So let's start with a diagram. It's accelerating, and it travels 16 meters. So we don't need to think about the force diagram here, but we've got the lift accelerating upwards, and if we fill in SUVAT, we could also get a question on this which links in the forces involved, but this one is literally just give me, it gives me the displacement, it gives me the time, and it gives me the final velocity. So literally we can just plug in these values here, and then we've got enough information to use SUVAT. So it travels 16 meters. Obviously, if we choose up to be positive, the lift travels a distance of 16 meters. A 5-second period, so the time it takes is 5. And it increases from u. We don't know what the initial speed was, but we do know that after 5 seconds, it's now traveling 4.2 meters per second. We don't know what the acceleration is, and we're not asked to find the acceleration, in the first part anyway. Okay, so we're looking for an equation which would allow me to find u. Okay, we don't know what the acceleration is, and we don't need to find the acceleration yet. The equation that we can use for this one is s equals a half u plus v times t, because this is the one equation that doesn't have an a in, and we don't know what a is. So we can say 16 equals a half u plus 4.2 times by 5, and then all we've got to do now is just rearrange this to figure out what the initial velocity was. Multiply by 2, divide by 5, and then subtract. Okay, that's giving me 1.9 meters per second. Then it does actually say to find the acceleration for the next 3 marks. So you want to find the acceleration of the lift. We can use any equation here because we know what the initial velocity is. So we could say v equals u plus at. We know it finishes with a velocity of 4.2. The initial velocity is 1.9. The acceleration is what we're trying to find. And the time it takes is 5. So if we do 4.2 minus 1.9 divided by 5. That should give us 0.46 meters per second squared. Apologies guys, I just noticed I made a mistake. I went from 4.2 to 4.5, like that should be 4.2. Obviously you can check the mark scheme. If that would have been 4.2, that would give us 2.2. Which then affects this answer. Sorry. So we get the acceleration to be 0.4 meters per second. Okay, the last question we're going to look at is for a velocity time graph. Okay, for this last question, we're given a diagram. And what I would probably recommend before you start the question, like just pause the video and actually try and visualize what the train, this is, the train moves on a horizontal track, straight horizontal track. Just think about what the journey of the train looks like what do these stages represent? Okay, so we can see that and during this point, initially the velocity here is 0, so the train starts at rest. And then for the first 18 seconds, the velocity increases. So the train accelerates, it gets faster, it gets faster, it gets faster. And then after 18 seconds, the train now begins to slow down. Slows down, slows down, slows down. And after 28 seconds, the train is at rest again. So in the first 28 seconds, it's sped up, slowed down, and stopped. Now for this last section, the velocity is negative. And don't forget, velocity is a vector. We think about positive is one direction and negative is the other direction. So essentially what's going on here is now between 28 and 38, it speeds up. It's got like a negative velocity. So it starts off going one way, speeds up, slows down, stops. After 28 seconds, the velocity becomes negative, so it speeds up in the other direction. So for between 28 and 38, it's moving in the other direction, it's speeding up. After 38 seconds, it begins to slow down. And then after 50 seconds, it stops again. Okay, so in this section, we're moving in one direction. In this section, we're moving in the opposite direction. Okay, the question, first of all, says find the distance in the first 28 seconds. So what we need to know about velocity time graphs, the area underneath represents the distance. Okay, so the area for this, we can think about the triangle. Base of the triangle is 28. Height of the triangle is 5. So the distance would be a half base times height. Let's see what that gives us. So that gives me 70 meters. Part B says calculate the total distance. Now we've got to be really careful with the term that's used. Total distance, it doesn't say displacement. So the total distance. In the second stage of motion, we've got another triangle. The height of the triangle is 5. The base goes from 28 to 50, so the base of this triangle is 22. So this area would be a half times 5 times 22. Which would give us 55 meters. So the total distance moved, not displacement, would be, well, in this section we moved 70 meters. In this section we moved 55 meters. So total distance would be the combination of those two things. You've moved 70 metres and then you've moved 55 metres. Okay, so that'll give us 125 metres. And then part C says calculate the average speed. So a triangle that we will have learned at GCSE, but is also really important in the A-level as it comes up. Don't forget your distance, speed, time triangle. If you want the average speed, it's distance over time, isn't it? So the total distance that we travelled was 125 metres. And the total time taken to do that was 50. So that gives us 2.5 metres per second. Okay, the next part D asks for displacement. Now if you think about this, if we draw a diagram, we started off, we were at rest, and then we moved 70 metres that way. But after 28 seconds, the velocity is 0. And then when the velocity is negative, we're moving in the opposite direction. So then you go back and move 55 metres in the opposite direction. So don't forget, displacement is like, essentially it's distance measured from where you started or relative to a position. So if you started here, moved 70 metres, then stopped, moved 55 metres, the displacement, in other words, where you were from where you started, would just be 70 minus 55, which would be 15 metres. Okay. Next part says the average velocity. So if we go to distance, speed, time, it's the same sort of triangle, isn't it? But the velocity, the difference here. Instead, we know speed is distance over time, velocity is displacement, because we're thinking about vector quantities here, aren't we? So velocity or average velocity is displacement over time. Now we know the displacement was 15 metres, and we know the time taken was 50. Okay, so that gives us 0.3 metres per second. Last part of the question, something else that we've not mentioned yet, but we need to know. So when you get velocity time graphs, we know the area underneath represents the distance. This one asks us for the acceleration. So the acceleration is just the gradient. So in the first 18 seconds, if you look at our triangle, we go from 0 to 5. So the gradient in this line, if you think about it as well in another way, in like a more mechanics way to think about it, acceleration is change in velocity, isn't it? So your velocity divided by your time. Velocity is measured in meters per second, acceleration is measured in meters per second, meters per second squared. So if we've got change in y, which would be 5, gradient, change in y would change in x. What you can think about is change in velocity over time. So the average velocity would be 15 over 8. Sorry, the acceleration, which would be the change in velocity over time, would be 5 over 18 meters per second squared. We could also write that as decimal. It's probably easier if we write it as a fraction, it's more accurate. But I think the mark scheme might use a decimal, so it'd be 0.27 recurring. I've just checked the mark scheme and it accepts either. It's probably better to leave it as a fraction, to be honest. If you are going to write it as a decimal, just make sure you use at least 4 significant figures. Alright guys, thank you.